Okay, so let us go a bit forward and comment a bit what I said. So first of all, I wanted to propose you this combinatoric argument. This was a combinatoric argument, and it is not completely elementary. So there is some complication. Other arguments are much less complicated than that, but you have to learn to think in terms of combinatorics, because first it is very important in probability and in statistics, and now probability and statistics is very well spread. For people studying physical engineering, it is quite important to use this way of reasoning, because it is extremely important. It is really one of the basics of statistical mechanics. Okay, so use combinatorics. Don't be scared of combinatorics. This is a combinatorial argument. So I think I explained really everything, perhaps too much, perhaps I was too pedantic, except one thing, and I want to dedicate a remark to this, and the question is, why is the number of permutations of J objects equal to J factorial? This is the question. Why is it? So the reason is very similar to the one we did at the end. So try to put J objects in J boxes. So permutations is equal of different ways to do that, to put J objects in J boxes. And we reason like before. So for the first object, one has J options, so J choices. For the second, one has J minus 1, and so on and so on. So for the Jth object, only one. So the number of possible choices, or the number of possible permutations, is exactly J options for the first object times J minus 1 options for the second object times J minus 2 option for the third object, and so on and so on. Okay, and this is exactly J factorial. So this is an example of elementary combinatorial argument. Of course, the argument I gave you for the previous computation is much more complicated. And now, armed with the Newton's binomial, we can go to prove the following proposition, which is the problem of monotonicity of AN, and the proposition says that the sequence AN equal to 1 plus 1 over n to the nth power is strictly monotonically increasing. Okay. So in the proof we use the Newton binomial. Remember that I told you that a direct proof is extremely difficult because there is a competition between the exponent that is rising with n, is increasing with n, and the base, which is decreasing with n. So the proof is the following. You have that 1, so an is equal, sorry, today I'm not so able to write properly. I don't know why. I try to be too fast perhaps. So an is by definition 1 plus 1 over n to the nth power. And so Newton polynomial says that this is the sum of j going from 0 to n of the binomial coefficient nj. Then you have 1 to the power n minus j and 1 over n to the power j. Let me write it in a more comfortable way. So this is the sum for j going from 0 to n of nj, and then here this guy here is equal to 1 and the other is 1 over n to the j's power. Okay? Now let us write the expansion of the polynomial, and the expression is n minus 1, n minus 2, up to n minus j plus 1 here. And here you have j factorial n to the jth power. And now I distribute all the factors in a way that makes all the expression easier to handle. So here we have just 1 over j factorial, and then I just distribute n to the j's. Here n to the j's means that there are j factors all equal. They are all equal to n by n by n by n, j times. So here you have j factors, but they are n minus 1, and so on and so on. So here there is a factorial, and then I write n minus 1, n minus 2, up to n minus j plus 1 here at numerator, and at denominator I put one n here, another n here, another n here, another n here, and we have j factors, all that are n to the j, and all that are j factors. Okay? And now I write it in a simpler way, just remarking that n over n, this guy here, is obviously equal to 1, so I don't write anything, and the other guy here, let me try another color here, is 1 minus 1 over n, and so on and so on. So here I have 1 minus 1 over n, 1 minus 2 over n, 1 minus 3 over n, up to 1 minus j minus 1 over n. Okay? And so this is an. I recall you that this guy here is an equal to all this expression here. That seems to be quite complicated, but it is not. Particularly, it is very well suited for our need to compare an with an plus 1, and this is what I'm doing now, because an plus 1, of course, it has the same expression of an, except that wherever there is an n written, this has to be substituted with n plus 1. There is a mistake, sorry, this is not n, this is j factorial. And good. This is an. So an plus 1 will be sum j going from 0 to n plus 1, 1 over j factorial, 1 minus 1 over n plus 1, 1 minus 2 over n plus 1, 1 minus 3 over n plus 1, up to 1 minus j minus 1 divided by n plus 1. Now compare the j's term here of an with the jth term of an plus 1. 1 over j is the same. And now let us just compare this guy here, 1 over n with 1 over n plus 1. And so, of course, n is less than n plus 1. This means that 1 over n is larger than 1 over n plus 1. This means that minus 1 over n is smaller than minus 1 over n plus 1, which means that 1 minus 1 over n is smaller than 1 minus 1 over n plus 1. And this is, of course, telling us that this guy here is less than this guy here. And exactly in the same way, you have that this estimates holds for every couple of corresponding factors. Okay, so notice that the j term in the sum, in the expansion of an, is strictly smaller than the jth term in the expansion of n plus 1. Moreover, this expansion of n plus 1 has one more term because it has n plus 2 term from 0 up to n plus 1. Here, an is made only of n plus 1 terms. So there is one further term that is positive. So, furthermore, the expansion of n plus n plus 1 has an extra term, an extra positive term with respect to the expansion of an. Then for all these reasons, we end up with an strictly smaller than an plus 1. And this is the end. So an as a sequence is strictly monotonically increasing. Good. So from the previous theorem, we know that it is regular, so it has a limit. This limit is finite if the sequence is bounded, and is plus infinity if it is not unbounded. And then the following proposition is about boundedness of the sequence and says that an is equal to 1 plus 1 over n to the nth power as bounded. Proof. Use again by Newton polynomials, Newton binomial. We have that an is equal to sum j from 0 to n. See the previous proof, and remember that we expressed an in this way: 1 over j factorial, and then times 1 minus 1 over n, 1 minus 2 over n, up to 1 minus j minus 1 over n. Now all these factors, except the first one, the factorial, are less than 1. So I have that an is less than sum for j going from 0 to n, 1 over j factorial. Okay? Good. Let us write 1 over j factorial. This is, of course, 1 for j equal to 0. 1 over 0 factorial is 1. And then there is plus 1, which refers to the term with j equal to 1, 1 over 1 factorial. Then we have plus 1 half to the first power, which is 1 half, plus 1 to 3 factorial, which is 1/6, 1 over 4 factorial, which is 1 over 24, plus 1 over 120, plus 1 over 720, plus dots. Okay? Now notice that here 1/6 is less than 1/4. Okay, I'm producing some estimates that lead us to the result. It's a sort of strategy. They are not the only estimate you can produce, but this is easy to do. 1/6 is less than 1/4. 1 over 24 is less than 1/8. 1 over 120 is less than 1 over 16. 1 over 720 is less than 1 over 32. So what I am doing here is to tell that indeed eventually, at least eventually, but not only eventually, we have that 1 over 2 to the power j minus 1 is less than 1 divided j factorial. Okay, this is what we are doing basically. This is because why j minus 1 and j? This is a matter of being precise. It is not the core of the argument. The core of the argument is that there is this relationship between factorial and exponential. Exponential is weaker than the factorial when going to infinity, as you probably already know from the exercise sessions. However, what happens here is that 1/4, this is 1 to the power 2 to the second, and here 1 over j factorial, which is 3, okay? So this is why here there is j minus 1, here there is j. Here 2 to the 5th, and here is 1 over 6 factorial. So let me write that this an is less than 1 plus 1 plus 1 over 2 plus 1 over 2 to the power 2 plus 1 to 2 over power 3 up to plus 1 to the power 2 over n minus 1. And this I can rewrite as 1 plus sum from j going from 0 up to n minus 1 of 1 over 2 to the jth power. Okay? Now, this is a geometric sum. With ratio less than 1. Okay? So we don't know anything about infinite series and so on and so on, but we want just to show that this quantity is bounded independently of n. This means bounded. an must be bounded. So we have to estimate this sum here, getting rid of n. And here it is not so difficult because one just has to consider this high school formula, perhaps also primary school, I don't know. High school formula that says that 1 minus x to the n is equal to 1 minus x and then 1 plus x2 plus x n minus 1. Okay? Very easy. This is how to decompose this binomial. So you have this factor, and then there is a polynomial which is not further decomposable, at least not if you use only real numbers. However, as a consequence, so if you don't believe this formula, just do the computation. Okay? At the end, you end up with 1 plus x squared plus x to the power n minus 1 is equal to 1 minus x to the n divided 1 minus x. This is good. And this is nothing but the sum, if you want to use the notation of the sigma, for j going from 0 up to n minus 1 of x to the j. So putting x equal to 1/2, you have that exactly the sum here that enters in our computation. So the sum, the sum for j going from 0 up to n minus 1, 1 over 2 to the jth power, this is equal to 1 minus 1 over 2 to the power n, and here you have 1 minus 1 over 2. So this means 2 times 1 minus 1 over 2 to the n, and this is less than 2, because this brackets contains something that which is less than 1. And notice that this passage is very important because here we get rid of n. And this is very important because now we can write an we can write that an is less than 1 plus 2 equal to 3. So an is bounded. And as a corollary, we have that being monotone and bounded, the sequence an equal to 1 plus 1 over n to the nth power converges to the supremum 1 plus 1 over n to the n, which is necessarily less or equal 3. Okay. What is the truth? The truth is that it is E. This is called E. Okay, so we can give here a definition. The definition is the Neper number. The Neper number is defined as E. The name is E. I don't remember why. Once I knew, but now I'm getting older, I don't remember just pure information like this. So this is the limit of 1 plus 1 over n to the nth power, which turns out to be 2.7a1.828182845 90 45 2 and so on and so on. Okay. Okay. And the remark, you know that E is irrational. I think we will prove it at some point, if I remember to do that. But we will need some Taylor's series. And this E as a sort of other alternative definition, you will see it at analysis 2, which is nicer. I find it nicer, so I tell you. The alternative definition is E is equal to sum of 1 over n factorial, as we tried to compute it, but for n going from 0 up to infinity. You have to compute all of them, you get it. Now it sounds strange because here 1 over n factorial seemed to be really a drastic approximation because we had to cancel all these guys here. Indeed, it was not so drastic because when n goes to infinity, then you have the truth. This is really 1 over n factorial. This is curious and you will study it in analysis 2. And I conclude this video with some exercises. Compute this limit. So with an, sorry, I don't have the pencil now, so just wait 1 minute. However, are limits that are easily derived from this one, from the definition of V. And the limits are an equal 1 minus 1 over n to the nth power, so there is a minus instead of a plus here, or 1 plus 2 over n to the nth power, or 1 plus 1 over n squared to the n, and this is quite difficult, and 1 plus 1 over n squared. This is easy. This is easy once you find the right way. Otherwise, it is very difficult. Okay, and now we change completely argument. We remain on the sequences, but we go on a very subtle